In section 6.7, we'll start looking at energy diagrams, which are probably better termed reaction coordinate diagrams, because the term energy diagrams is very vague and can mean a lot of different things. But if we look at a diagram, so what we're going to look at is we're going to see the energy on the y-axis and reaction progress, and I've kind of drawn a couple of these already, though we didn't talk about them in detail yet, on the x-axis. So the idea is that if we start somewhere, just pick a place to start, that's our starting material or our reactants, we're going to go through some kind of an energy change, and it always is higher energy first to break bonds, and then somewhere at the end we end up either with higher or lower Then as we go through, we'll either end up somewhere at higher or lower energy in our products, depending on the type of reaction that it is. So there are some important pieces of this to point out. This top part here is called a transition state, and it's symbolized by a double-crossed arrow. This top part here is called a transition state, and it's symbolized by sort of like a double-crossed T. And that's the highest energy point along the path. So that would be a transition state. We also have the energy from the starting material to get over this transition state. So there's an energy amount that we have to get over to make a reaction occur. And that's called the activation energy, which is written EA. And activation energy is always going to be positive. There is always some energy barrier to make a reaction occur. It can be a small energy barrier or a large energy barrier, but there's always an energy barrier. And then we have the energy difference between our starting material and products, and that's delta H of formation, or heat of formation. Enthalpy of formation. And there, if the energy of formation, or delta H, is negative, that's going to be exothermic. So in this case, it would be an exothermic reaction. And we could also say, if we wanted to think about K, our products are lower energy, so products are favored. And our K would be greater than 1. And this example that I just drew is a concerted reaction. It all occurs in one step. Now I can also look at another kind. Draw another one over in this corner. And let's look at one that would be a stepwise reaction. So in a stepwise reaction, we also started our starting material. We go up through some kind of transition state, but the difference is we stop somewhere in the middle before we go back down to our product. So here I've got my starting material, here I've got my product, but here in the middle I have something that's called an intermediate. And that's a lower energy, so here's highest energy, here's a low energy, or a local minimum. So this local minimum is our intermediate. So I go through a really high energy transition state, I come down to an intermediate, I go through another transition state, then eventually I come down to products. So that would be a stepwise reaction. The activation energy is here. And the delta H is still from the starting material to the product, here. And that would be a stepwise reaction. Now this one is still exothermic, and it still favors products. And K is still greater than 1. So now there's a variety of different types of reactions that we can draw, and I'm going to challenge you to draw some on your own here. So first I'm going to have you do a concerted reaction. That's endothermic. There are several different ways to address this on quizzes or exams, and that is to say, draw an endothermic concerted reaction. Another way you could say it is draw a concerted reaction that favors reactants. And a third way to say the exact same thing is you can say it's a concerted reaction where K is less than 1. So given this reaction coordinate diagram, go ahead and pause the video and try and draw a concerted reaction that's endothermic. We start with reactants, we go through a transition state, we do not have an intermediate, and we end at products. The reactants have to be lower than the products in energy, and energy has to go into the reaction to make it happen. So our delta H would be here. And delta H is positive, which means that it's endothermic. The reactants are lower energy than the products, so that favors reactants. And K is less than 1 means the same thing, that reactants are lower energy than products. So again, we have energy on the y-axis, and our x-axes are going to be reaction progress. So what I want to look at are two reactions that both have the same delta H. So I'm going to pretend that this delta H and this delta H are identical. But now we have different activation energies. And we have to consider how that changes our reaction. Now, equilibrium is completely based on delta H. So at delta H0 defines equilibrium, or how much of each product is favored at equilibrium. So that defines what's going to happen in the end. But what's going to happen with EA? So if we want to think about energy distribution and temperature. So I've got a given temperature. So let's say that T equals 25 degrees C. That's at standard room temperature. Every molecule in the sample does not have the same energy. So if I look here, this is the number of molecules. And this would be the energy of each molecule. And there's going to be some kind of a Gaussian distribution of the energy of each molecule. So if I look here, here's the center point, and so this relates to 25 degrees C. However, some of the molecules in there have much more energy than that. And a great example of this is if you think about water evaporating out of a glass or off the counter at below boiling point. So why does water evaporate out of a glass or water evaporate off the counter if it's not boiling? Well, the reason is that some of the molecules have enough energy to become a gas. While the majority of them don't. So the sample is not boiling, it's not quickly becoming a gas, but gradually a few of these molecules become a gas and then it re-equilibrates, and then a few more molecules become a gas, then it re-equilibrates again. Now, if we raise the temperature, what happens is this set point moves. And if this is the cutoff for having enough energy to become a gas, if I raise the temperature, a lot more of my molecules have enough energy to become a gas. So if we can apply that same thing to reactions, in this reaction here, there's a very small energy gap that's needed to be able to cause this reaction to happen, to move from reactants to products. Okay? If that's a small energy gap, that means a lot of the molecules, it'll be like this down here further, a lot of the molecules will have enough energy to get over the gap. If it's a higher energy gap or a higher activation energy, it might be up here somewhere, where less of the molecules have the energy to get over that. So it's going to be a much slower process. So this is the idea of if you watch your water evaporate as it's boiling, this would be as you watch your water evaporate at just room temperature. Eventually, the water's all going to be gone either way. That's the equilibrium. Okay? Eventually we're going to get to the same point because of whatever our delta H is. But how quickly we get there is going to be based on how big this gap is, the activation energy. So activation energy is going to define kinetics of the reaction, or the rate of reaction. So larger EA equals a slower reaction. Smaller EA, in this case, is going to be a faster reaction.